I want to look at these two sets of outputs next to each other again. Let me do this. So I'm going to summarize the ANOVA. I want to point out that if I, instead of saying summary m1.lm, say ANOVA m1.lm, so in other words, if I use the ANOVA function and give it the output from the regression, I have to hide the whole thing, it gives me back exactly the same table. Okay? So again, this is the summary of the ANOVA. This is ANOVA parentheses output from the linear model. These are identical. Right? So what I'm showing you is that you can run it as an ANOVA or you can run it as a linear model, but either way, the coefficients are being estimated and the sum of squares ANOVA table is being calculated. The difference is the default in what's usually shown. I also want to, as we're looking at this one more time, have it print out the usual summary of the linear model that is here. So I want to compare it again to the ANOVA output. In particular, I want you to see that this ANOVA right here, which is testing the null hypothesis that the means are the same in each group, is the f-test that's summarized on the bottom row of the regression. So everything that's relevant about the ANOVA table actually does come out, in this case, as part of the regression output. We've got our F statistic, 1.77, on 4 and 8 degrees of freedom. Here's degrees of freedom. We've got our p-value, 0.1432. There it is, right? The bottom row of the regression, by default, will compare the model you specified to the equal means model. And that's, in this case, with only one predictor, that's the same as saying, are the means the same in each group? That's the equal means model compared to this alternate model, the separate means model, where there's a different mean in each group. So again, the very bottom row of the regression output gives the same thing, in this case, that you'd get if you just did the ANOVA, because this is a test for whether this model is any better than an equal means model. And that's exactly what the ANOVA was asking as well. So in this case, there is nothing new to be learned, from running both the ANOVA, showing both the ANOVA output and the regression output, because the ANOVA output is actually summarized as part of the regression output. In fact, there's nothing mysterious about the values in this regression output. So we said that this is just a repeat of what went in. This is the summary of the residuals. We talked about the coefficients. We talked just now about this row on the bottom. What about these other two rows? There's only 2 more rows in this regression output that could possibly be mysterious. So first I want to point out that the residual standard error is the square root of sum of squared residuals over degrees of freedom. So let's think about the ANOVA table again. Here's our sum of squared residuals. Here's our degrees of freedom. If we take sum of squared residuals divided by degrees of freedom, by definition we get the mean square error. Okay, so here I'm going to calculate that. Earlier I calculated sum of squared residuals. Now I'm going to divide that by 78, that's the appropriate degrees of freedom, and get the mean square error. And if I were to look at that, I can see that's 0.267. Lo and behold, that's the same mean square error shown in the ANOVA table. And if I were to take the square root of that, 0.517, that's the number shown here. That's the residual standard error. So these two different sets of outputs are just choosing different ways to show you the amount of error there is, either by the square root of the sum of squared residuals over degrees of freedom, or by just showing you degrees of freedom, sum of squared residuals, and the mean square. So now this row is not mysterious anymore. This is the same thing that's shown in the ANOVA table. What about r squared? Multiple r squared just means r squared. There's nothing, that word multiple contains no information. So, but one of the definitions of r squared is that it's the sum of squares due to the model divided by the sum of squared total. And we calculated these two quantities previously using the ANOVA output, using the residuals from the ANOVA, in fact. So if I take the ratio of those two, I get 0.083. That is the same as the multiple r squared. So this multiple r squared shown here is literally sum of squares due to the model divided by sum of squared total. Another way to say the same thing is it's 1 minus proportion of the total sum of squares due to the residuals. So that's exactly the same number. And we can confirm the adjusted r squared as well using the formula for that. So it's 1 minus sum of squared residuals divided by its degrees of freedom over sum of squared total divided by its degrees of freedom. And now I can confirm the adjusted r squared as well. There's this number and this number. So there's nothing mysterious anymore in the regression output. And any of the values here we can calculate looking at the residuals that pop out when I run it either as an ANOVA or as a linear model, because those are the same thing. Next, I'm going to run a model that looks at log sleep by a different predictor, in particular log weight. So let's look again at the plot of log weight and log sleep. Here we go. So we've got this negative correlation. I can try to make a box plot of log sleep by log weight. That's just going to look silly, just to point that out, because log weight is a continuous variable. What it's trying to do is, for each different value of log weight, show a box plot of log sleep, but every animal has a different value of log weight, so that's not working particularly well. These are all lots of tiny box plots, just to show you that doesn't always work. However, if I round log weight and make a table of it, then you can see if we round weight, well, there's 2 animals whose log weight is rounded to -5, 5 animals whose log weight is rounded to -4. Now we actually have some groups, and so now I would be able to make a box plot if I wanted to look at the distribution of log sleep by a rounded value of log weight. This shows you the same sort of distribution. I like this plot in addition to the scatter plot because it emphasizes the idea of what a regression is doing. Even for a continuous variable, the regression says, fixing a particular value of the predictor, what's the distribution of the outcomes? So you can think of a regression in the same way we thought of f-tests for ANOVAs, where the x variable, the predictor variable, is just breaking down the data into groups. But let's go back to this plot because that's the one we're actually going to study. This time I'm going to start by running the regression because that's the thing that comes naturally when we're thinking about a continuous predictor. So I'm going to go ahead and run that, and then I'm going to summarize it. And of course what I'm going to get is the type of output I expect to see from a linear model. So I have an intercept and a slope, right? And p-values for each of those. I also have an f-test. So that's interesting. We'll come back to that. I've got my r squared, and I've got my residual standard error. I can make a plot of residual versus fitted values just as I could before. Right there it shows up. We can decide whether we like that plot, but right now the point is that we can make it. Okay. But I'm going to go back to the original plot and add the regression line to it. So you can see that's a reasonable line, and it has the intercept and slope that are specified right here. So this seems like a pretty standard thing to do for a continuous data set like this one. Now I'm going to do the thing that may seem counterintuitive if you're used to dealing with continuous predictors. I'm going to run an ANOVA instead of an LM, a linear model of log sleep on log weight. So I'm going to run that and look at the output for it. And of course the output now will be summarized as an ANOVA because that's the default for an ANOVA. Okay, so what is this? So let's look at this output, and I'm going to just, so we can compare it again, summarize the regression output. Okay, we've got these two. The first thing I want you to note is that these p-values are identical. So the p-value that came out of the ANOVA for log weight is identical to the p-value that came out of the came out of the regression for log weight. What is the ANOVA doing? What is it showing us? Well, it's showing us that sum of square residuals. It's showing us the sum of squares that seem to be due to the model, so total sum of squares minus sum of square residuals. And it's comparing those to tell us how likely the data would be under the null hypothesis that the equal means is true, as opposed to the linear model. The way to tell that the variable that was used here as a predictor is continuous, its degrees of freedom here is equal to 1, as opposed to a larger number reflecting the number of categories, minus 1. So when you look at the ANOVA output, what this is telling us is that this data would be really surprising, the p-value is essentially 0, if the truth is that no matter what the log weight is, the log sleep would be the same. This data would be shocking if the truth is that log weight is not actually a predictor. Rather, the regression model seems more compelling. That's exactly the same question that's being addressed by the output from the regression. This right here, we usually talk about, the one I've highlighted, we usually talk about it as a test for the null hypothesis that the coefficient for log weight is equal to 0. But that's the same as saying that under the null hypothesis that an equal means model is correct, this data would be surprising. If the coefficient for log weight is equal to 0, then that means the equal means model must be true. In other words, the slope must be 0. Just one horizontal line must be the right line. And this p-value is telling us this data would be really shocking if the right model is just one straight line, one equal means model. So these two sets of output are answering exactly the same question. That's why it's the same test. The p-values are identical, and in fact, if I were to take the square of the t statistic shown here, I get 54.58, and in fact, that's the f value that's right here. So it's literally the same test. The t squared is the f. The p-values are exactly the same. In the case with one continuous predictor, the ANOVA p-value is exactly the same as the p-value for the t-test for that predictor from the regression output. And so we can also see then this is the same f-test, the same results of the ANOVA, typical ANOVA format, shown at the bottom of the regression output. Right, this too is the same. It's different rounding, but this too is the same p-value. Here's a 54.58. That's this t statistic squared. Remember that the f-test shown on the bottom of the regression output is always going to be comparing the model you ran to an equal means model. And in the case of only one predictor, that's the same question being asked by this line here. It's comparing the model I actually ran to a model without this one predictor, so an equal means model. So this line is a summary of exactly this f-test, which is exactly identical to this t-test that we have right here. I can go through the same process I went through before if I like to verify the sum of squared residual and the sum of squared model. So if I take the residuals from the linear model, square them, add them up, I get the sum of squared residual that is equivalent to what I saw in the ANOVA table. And if I take sum of squared total minus sum of squared residual, I get sum of squared model. My sum of squared model is also identical to what I saw in that table. And I want to show you just again that if I ask either of the sets of model output for the coefficients, I get the coefficient either way.